Before I start off, just a little bit about Bloomberg and me. Bloomberg, as you might be aware, is a technology company whose sort of strength and focus is data. Our primary product is what we call as the Bloomberg Terminal, or the sort of Bloomberg Professional Service, which is like a combined function and a workflow for people in the financial industry. But these days, we have been expanding beyond finance as well. I mean, like we sell the terminal to governments and lawyers, et cetera. And we also have other products apart from the terminal itself. We have like vertical portals for, again, lawyers and governments and so on. So there are a wide variety of products for many professional disciplines. As for myself, I started Bloomberg sort of 8 years back. I've been in news all along, and I'm now the team lead for the news search. My team is responsible for the search, alerting, and ingest platform infrastructure that we have for search. We started with Solr Lucene 3 years back. We used to have a proprietary software before that, and I'm now a committer of the project. And this talk is going to be more about sort of like the kind of challenges that we face during this process. What are the sort of what are the roadblocks we ended up in, how we ended up solving them. We are, as I said, like we started 3 years back. We are actually in the middle of releasing this entire migration to clients. So it's been quite a journey so far. So before we get started, right, I mean, I think when you think of search, a lot of different things come into mind, right? And I think the same applies for news search as well. It's just search on news, really. So there's an entire ecosystem surrounding this, and a lot of different pieces. So the way you look at search is that you have a screen, you have a box in front of you, you start typing into it. As you start typing, the system sort of suggests queries as the user is typing, and then you enter something, and then you press enter. At that point, there's a system which tries to understand what you're talking about, right? I mean, like you might type in something, and you might expect the system to actually make sense out of it and give you a more structured query. Here's where things like natural language processing or entity recognition, spell check, et cetera, come in. At the end of it, you essentially have like a structured query, which has like keywords and potentially other metadata as well. I mean, in case of news search at Bloomberg, you might have like searches which span sort of companies or topics or people or other such things. So you have like a structured query, which is got out of this unstructured input. You search on that, you get documents, and then depending on the use case, you might be sorting those results by relevance or by time. Both use cases exist in Bloomberg. And then and this is where the interesting part comes in, especially for Bloomberg. We need to alert users when new stories come about for search as well. So it's a dynamic screen. You have the initial set of results. As soon as any new story matches your search, that needs to be alerted out and needs to scroll into your screen, so as to speak. And then you can do other things like, I mean, expose facets and recommend searches and search results. A lot of this talk today is going to focus on searching of the keywords. So we assume that the search has already been done for us, and then we sort the documents, and then we alert new users. And even though the migration might have involved other components apart from that, I think this is sort of like, and even the alerting, I don't think so I'll go into the detail. I'll probably sort of show a slide towards the end. I think there is enough to sort of fit a talk just for just the searching and the sorting part of this. What do we deal with, right? I mean, I think there are lots of different search problems, and I think during this conference you probably have seen quite a few use cases. Why do I have a unique story to tell? It's because like we service over 320,000 customers or so. I think it's now more 350 odd near that. We get around 8 million searches a day, right? I mean, and we get a huge volume of news stories. A news stories could be like 4 kilobytes in size, or it could be a huge PDF attachment with 8 megabytes in size. And we get sometimes at peak, we get around 500 stories per second. Now, the challenging aspect of this is that for any search, we need sort of like an average latency of search response latency of around 100 to 200 milliseconds. Now, that by itself is possible. A lot of people have done that. The additional challenge we have on top of that is that it's a real-time search engine. So as soon as any story becomes available for search, we need to expose it for search in around 100 to 200 milliseconds. Why is this important? Like, why do people care? Because our primary use case here is with traders. These guys sort of like want to know news as soon as it has happened. So they actually lose money if you end up being late on their search results. So it's quite important for them that they get to know as soon as there's an unemployment rate change, they need to know about it. So that's the search part of it. The alerting part, which is kind of the reverse of search, where you have like lots of searches. For every incoming document, you need to find out which searches actually match this document. That's a real-time feature as well. So as soon as a story gets published, we need to tell users about it in around 100 to 200 milliseconds again. So we, at any point in time, we have around, say, 1 to 2 million searches saved in our system. So these are either people just running the search screen. So for every search screen you run, a subscription gets added in the backend saying that I've shown the initial set of results for this search, but whenever a new story matches, please update the screen. Or it could be offline. I mean, I might not be running the screen actively, but I might say, hey, here's a search. I want all important news on oil. And every time a news story comes in, send me a message or show me a pop-up on the screen or play a sound or read out the text in the headline as a text-to-speech. So that's the sort of like the statistics part of it, like what makes this quite hard to do. In particular, we used to have like an existing system which used to do that, I just mentioned. Around 3 years back, we realized that this is sort of quite inflexible in what it does. So we decided to move to Solr Lucene. I mean, we had evaluated various other alternatives. We chose Solr Lucene mainly because it's like, sort of like rich in features, it's extensible, it's actively maintained. We wanted something which is free as in software, as in a development cycle. I mean, I think that distinction is quite important to maintain. When I say free as in software, it's free for us to modify and use in the way we want. Free as in development in the sense that we have a say, and that's something which is sort of like guarded by the Apache Foundation, that we have a say in how the development goes. And we had to, as a part of this process, we had to actually build from scratch an alerting backend based on Lucene. The migration is not just sort of like a pure migration from one backend to another. In some sense, I think what we have achieved is that we have ended up with an architecture which is sort of extremely scalable. I think we reached a place now where I can easily add like 50% more hardware than on top of what we have and expect a 50% increase in sort of like performance or sort of load or number of stories. And that's something which is easily possible. I just need to add those machines, bring it up. And a lot of the work that I think Solr has spent over sort of having the Solr cloud and making it elastic has gone towards this to be in a position where I can easily do this. So as with any search engine, there are two aspects to a search engine. There is something called a document, there's something called a query, right? You have a set of documents and you have a query. In our case, a document is a news story. News story is kind of like a loose umbrella term. It could be just something news, really. It could be research documents, someone saying that this is the reason why you should buy stock on this company and giving the explanation for it. Or it could be social media, like tweets, for example. But all of these have like a particular structure to it. They have like a story body, they have a headline, they have a time of arrival, source, attachments, etc. Around 10 to 20 different metadata fields. And they also have like tags, and these are quite important, right? We have systems in the background which essentially, based on the content of the story, derive tags for the story, like companies or topics or people. Which are the companies associated with the story, or the topics or the people associated with the story? So this is all the metadata which is surrounding this, right? And what we can do is pretty much sort of construct a query which has arbitrary complexity. So when I talked about sort of like the 8 million searches which come in a day, it could be as simple as give me news on a particular company, or it could be as complex as this, which sort of like involves multiple fields, like Boolean operators, phrase searches, wildcard searches, like range queries, like this being this time and this time. Overall search filters, I want news only in English and German, but not other languages, or something like that. And beyond this basic set of features, some of the interesting challenges is, as I mentioned, some of these searches are really, really complex. I mean, I have seen searches sort of which are 20,000 characters or more in size. I mean, like, why would someone do that? I mean, but people do. There are people sort of like who have constructed their search over years of experience and almost consider their intellectual property. It sort of exists, and we have to sort of accommodate for them. But there are many sort of like places where this is actually easily possible using the UI as well. So for example, I might be a portfolio manager who's interested in around 1,000 different securities, right? And so my search would be sort of like, give me all news I'm interested on securities I'm interested in. That easily translates to a Boolean query of like 1,000 companies, thousands of companies, right? I mean, and that's an interesting challenge by itself. The other interesting challenge is that we sort of aggregate news from over 125,000 sources. The biggest one being Bloomberg itself, because Bloomberg is also a media organization, it's a news organization, but we have news from over 125,000 sources. The interesting aspect of this is that any user is sort of privileged only for a subset of these, because many of these are paid content, they need to have a subscription, etc. And on top of this, even if you're privileged, you might not actually be interested in that. I mean, I'm a guy who's sort of like old style, and I don't like social media at all. Never ever show me Twitter, even though Twitter is free. So in reality, on top of the search, you have to sort of filter based on this sort of like access control list, which can span sort of tens of thousands of sources. And then we have searches and stories in 40 languages, which is a challenge by itself. Solr does a great job in sort of like searching across multiple languages, but there are edge cases, and you have to sort of like every search case is different, so there's a fair amount of customization which goes into this. The search cloud that we have, we use Solr Cloud. Currently, we are on 4x, but we are looking to move to 5.3 pretty soon. Lots of Linux machines, like hundreds of shards, thousands of Solr cores. We often have to have multiple tiers, right? I mean, like we have what is called a recent collection, which tries to have data up to a few days old. And then if you're not able to satisfy that, this is the case with, by the way, with time-sorted results. As I mentioned before, we have two use cases, two predominant use cases. One is time-sorted results, the other is relevance-sorted results. With relevance, it's a harder problem to tier indices this way because you often might have stories which are older but more relevant. But for time-sorted results, it's easy optimization to say that I will first try a smaller collection which has only a small number of stories, and if it doesn't match that, then I'll go for the bigger collection. And then we have cross-data center redundancy, which is an interesting challenge by itself, given that Solr is not data center aware as yet, so we have to sort of like come up with this, and it's an active place of work, really. So as I mentioned before, stories are available for search in 125 milliseconds. This is by far one of the most challenging problems we had during this migration. Some of the side effects of this is that we practically have no caching whatsoever. I mean, it's pointless to cache something when it's going to be expiring in 125 milliseconds. And we have custom components for almost everything. I mean, for parsing, I'll sort of cover some of this in detail, for indexing, for searching, for what is called post-filtering because of the privileging model that we have. So let's go into some of these details, right? I mean, and this is where sort of like majority of my talk is going to focus on, sort of like, it's going to be a war story, really, on sort of like kind of challenges we have faced so far. As I mentioned, like we have this complexity in the query logic already present, and so as a result, we already have like a query syntax which is pre-existing in use at Bloomberg. And it's a pretty complex query parser, as I said. I mean, and one of the things we discovered was that there is no single query parser in Solr which actually had all the functionalities that we needed. You have some which had some parts of the functionalities, some others which had. But the other reality is that, I mean, people, especially the power users, fortunately not 99%, but the 1% of the users, actually do like the flexibility of being able to construct this search in the query syntax possible, right? I mean, so like things like this, for example, they would want to construct this using a free-form entry. So you can't, it's a harder challenge to be able to sort of like just take that away from them. So as a result of that, we had to have something which understands the in-house search syntax. On top of that, as I mentioned, we have like a sort of like a taxonomy of topics and companies and people. And there are sort of like validation and privileging logic on top of these tags as well. Some people are not allowed to search on certain tags. And this sort of like information is present in a database, which we needed to validate. I think one of the more interesting things is that, I mean, Bloomberg News has a feature called smart sourcing, which essentially means that my initial search is going to sort of like span a subset of the sources because that's what I think is the most relevant for the user. But let's say the query has something, like, I mean, let's say the query has company : Google in it, and let's say Google's blog is not my set of search sources. Just because you asked news on Google, I'm going to add this particular source on top of what I usually do. Right? So there is logic which says that I need to parse the query's tree to figure out what kind of entities are being referenced and then adjust my sourcing a bit more to sort of like give you more relevant results. So how do we do this? What we realize is that for maximum flexibility, especially given our custom queries and all this functionality, we will parse this entire query outside Solr, and we will make it into a tree and decide what the Lucene query should be. So once we decide what the Lucene query should be, then we sort of serialize that into using what is called an XML parser. By the way, There's one version of this in Lucene already. We had to make a modification and enhancements to it to make it more compatible with Solr so that it understands things like the analysis chain and so on. And what this allows us is that, we can even do things like, have a custom query type now. I can just sort of like convert that to an XML and actually get it executed without too many changes to the query parser. Some changes are needed still, but it's fairly easy to add new query types or have complete control over what the exact Lucene query is. By the way, I'm kind of assuming that there's some of you at least know the difference between query and query parser, but a quick overview is that a Lucene query is like a Java object, which is what is actually run on the search index for you to get back results. A query parser is just a string. A query is just a string, and a query parser typically converts a string to a Java object. So this is a XML query parser, which takes an XML and converts it to the query object. On top of that, I think the more interesting thing was that there are some queries which until recently was not even possible in Lucene, especially when you had things like, for example, a wildcard or a phrase query, which has to be near another wildcard or phrase query. What this N5 means here is that anything beginning with the tags should be near 5 words of incentive. And this entire expression should come after within 10 words of state or anything beginning with state. So NP10 means prior to this. So state should appear before tags or incentive. And then this entire thing or the phrase sales or news should be near this. This is not something I'm cooking up. This exists actually. There was actually sort of like, if you look up GitHub at flag search Lucene Solr intervals, there's actually a fork of Lucene which has support for these kind of functionalities, which is what we currently use. But the good news is that with 5.3, we actually scheduled some work to push this back upstream, and that's actually now gone upstream, and so we can start using this once we migrate to 5.3. One of the interesting challenges is how we search for the tags that we have on news stories. So the story here is that, I think each news story has like hundreds or tens or hundreds of tags associated with it, like companies or topics or people. And these are decided by an external classification system, which gives you an idea of this story based on the content that it has is, let's say, 70% relevant to oil or 100% relevant to some company, right? And so this is a score it gives, saying based on the classification output, it gives you a score saying that this is the relevance values for each of these tags. Now, these need to be used in 2 ways in our system. Even when you have like a time-sorted search, I might want stories which are about oil, but only if they have a relevance of 70 and above. I don't want like stories which with very, very sort of like marginal relevance to oil appear in my search results. The other important case is that, let's say I'm sorting by relevance and I'm asking for stories on oil. I obviously want stories which have higher relevance to oil to appear on top of my search results rather than the ones which have a lower relevance. This has multiple solutions, and I think especially with sort of like newer versions, sort of like there are more solutions now available with things like block join and stuff. But one particular solution which sort of like very nicely modeled the situation we had was, what we ended up doing was that we started treating tags as kind of keywords. And if a tag has a relevance of, let's say, 70 out of 100, we kind of treat it as if the same word appeared like 70 times in the story. This is based on, I don't know how familiar you are with sort of like TF-IDF. What sort of TF-IDF scoring model for keyword says is that the more occurrences of a keyword you have, the higher its relevance is, right, for that given keyword. So what we ended up doing is that we ended up repurposing this concept for tags, and we pretty much said that if a story has sort of like more relevance for oil, we will count it as if it has more occurrences of the word oil in the story, right? So this also allows for a nice normalization that TF-IDF provides, and also allows you to sort of like normalize keywords with these things, right? I mean, like if you have a search, let's say, a keyword Obamacare or topic oil, right? I'm just making something up. Then you need to make sure that stories on Obamacare don't trump all your search results. At the same time, stories on oil don't trump your search results as well. It has to be a good combination of the two. And this normalization essentially gives you that capability because keywords are pretty much like tags, and you can do this. The way we do this is that we have a custom filter at the indexing pipeline. So whenever sort of like an input comes to for a document saying that this is topic oil at tag 70, it actually sort of like adds 70 different occurrences, and it's quite easy to do that using some custom code. So if you think about sort of like the 3 years we roughly spent on sort of migrating to Solr, I think I would say that around 75 to 80% of the functionality was probably done in the first year or so. Roughly around 1.5 years after that, we probably spent sort of optimizing these searches. And that's probably the reality of any big search backend. You probably spend less time actually developing the functionality and more time actually optimizing it. There's no point having all this functionality when at the end of the day, with the initial prototype, like the average search time is 30 seconds, when what we need is around 100 to 200 milliseconds. So the next 1.5 years was actually taking it from a mean average of 30 seconds or completely falling down. That's the other alternative, at which time you don't know what the search timing is. It's kind of pointless at that case, to getting to an average search latency of around 100 to 200 milliseconds. And actually, I think we have outdone ourselves now. It's around less than 100 milliseconds in many cases. There were some really interesting cases with this, right? I mentioned about ticker list searches briefly, where a person has like a huge list of tickers. I want to sort of search on all any news about any of this company. As you say, it's logically a Boolean OR of like thousands of terms, right? But on top of that, you have this additional complexity that I just mentioned. I don't want any news on all these 1,000 companies. I want any news on 1,000 of these companies, so as long as they have a relevance of 70 or above. If you want to do this, then you need to, if you construct this at the Lucene level in a very naive way, you have a term query for, let's say, company A, and then you filter it by its term frequency between 70 to 100. So that's one block. Then another block for company B, and another relevance for 70 to 100. So on, 1,000 blocks, right? And as you can imagine, that's pretty slow. Here's where our parser's flexibility comes into place. What we pretty much ended up doing was went through a few steps by which we could actually sort of like write our own custom Lucene query, which did this in one shot pretty much. So you have one Lucene query which did this entire sort of like gigantic expression in one shot, and needless to say, the performance benefit was like substantial. The other interesting thing is that, especially for time-sorted results, the naive way sort of like Lucene does search is that Lucene's search index is divided into segments, and each segment has posting lists and inverted indexes and so on. The way Lucene does search is that it finds out all the documents matching your search for a given segment, then sorts them by your sort order and gives you the top 20. There was an interesting change to Lucene sometime in 4.4, I think, where we introduced what is called an early termination logic, where essentially when you have your index which is created, what if you had sorted your posting list, or you sorted your documents in the posting list by approximately the order which you would most likely use. So let's say you want in descending time order, all the documents for each posting list is sorted in descending time order. The advantage now is that when you're actually trying to search for this in descending time order, you don't need to actually sort or even go through the entire posting list, read the entire posting list up. You can read the top 20 and then cut off at that point saying, I've got my top 20, because it's already sorted. This thing was actually present in Lucene, but not in Solr. So what we went ahead and did is made it a pluggable aspect of Solr and added supported on the search side so that it can actually use this early terminating sorting collector. I think it's pretty close to being committed now. We just need to add a couple of unit tests and so on. The other big thing which sort of contributes a lot, especially in our case, is because, as I mentioned, we have like a commit interval of around 125 milliseconds. We make 8 commits every second because that's our index to search latency. That obviously means that, especially the way Lucene works, is that it creates lots and lots of small indexes and tries to search in them in sequence. And this can be pretty expensive as time progresses. Now you have something called a merge policy, which in the background tries to merge these segments into bigger segments. But the defaults are obviously what is not tuned for something which sort of commits at this fast an interval. So we had to be quite aggressive with our merge policy, and we had to spend quite some time trying to tune that further so that we can actually reduce the number of segments on disk to a manageable number. essentially it became an exercise in how much can you squeeze out of SSDs. Goes without saying that all this is on SSDs. I mean, we would have never lived to see the day even if it had been a spinny disk. Essentially, it became an argument on how much can you afford in terms of I/O so that you can make your search faster. There is a sweet spot somewhere. You can't do this endlessly because you will end up spending too much time doing I/O and not doing search. But it's an interesting exercise to find out where your sweet spot is. And I would certainly recommend if you have like a complex in a search system where performance is a priority, certainly do optimize your merge policy, and you will see the results as a result of that. One interesting change, I think, in recent versions of Lucene is that it actually, at least on Linux, tries to detect if your index is on SSD and tries to optimize it, because even the defaults could be very different between an SSD and a spinny disk. An SSD can take a much higher merge rate than a spinny disk. But that's just the default. You would need to tune it sometimes. So I call these changes as partly sort of the chapter 1 or the phase 1 of our quest for performance. Pretty soon you reach a point where, okay, you've done all these major things and you got the performance, but it's still not there. You still have low enough. And that's where you end up sort of like seeing how much sort of like, especially when you have such a high commit rate and you have so many documents coming into the system, that's when you start seeing the real effects of garbage collection in Java. That's where it sort of finally hits you. And you realize that even sort of the smallest inefficiencies can actually scale that hard. For example, I mean, there was one ticket in which sort of like we just removed one object which was being constructed with every search. The problem was that, I mean, like we have like lots and lots of shards. So that object was created at every shard for every search. So for every search, it was like kind of creating hundreds of objects. Now you have like hundreds of searches going on. So in every sort of like second or so, you have, at any point in time, you have like 10,000 of these objects created. When in reality, only one was needed per search. So a small sort of like optimization or refactoring of that code actually could give you a significant sort of performance benefit because it reduces the GC overhead. At some point, though, you realize, I mean, so we went through a lot of these iterations. I mean, like finding all the places where you would have inefficiencies in your search and inside Solr and sort of like modify Solr to sort of like do this. At some point, you realize that, I mean, yeah, you could do that. You can get GC to a manageable level. You can tune your GC and so on. But it's a reality of life that GC has to hit you, right? I mean, sooner or later. Which is where sort of like you have to start thinking about, can you route smartly? I mean, the way Solr does routing by default is that your search enters, it goes to one shard, and then it splits out to all the shards which have this. Each shard has multiple replicas. The replica it chooses is completely random. Now, especially when you're in a situation, as we did, where multiple replicas, multiple shards are co-hosted in the same JVM, as is, you have to sort of like strike a balance there anyway. It's no requirement that multiple shards can't be in the same JVM. If you have multiple shards present in the JVM, if you have completely arbitrary routing, the chances are that you will hit probably all the JVMs you ever have in the system. That's not good because now there is a probability that any of these JVMs would be running GC. That means that effectively the chances of you hitting the JVM is n times, where n times what it can be because if you have n replicas. So one optimization we did was to see whether when the federator or the initial shard chooses the shards for routing, it could try to see whether, okay, for shard 1, I have sent the request to JVM 1, and I know that shard 5 and 9 and 13 are also in the same JVM. Now that I have chosen JVM, anyway I'm going to sort of hit the probability that it is going to go through JC, might as well put all of them there. So that way you reduce the probability of you hitting a GC as a part of a search request by a factor of n, where n is your replica count. Why is this important? Because like at the end of the day, the last shard which comes back determines the time that takes for a search. If you have a really slow shard and everything else is fast, doesn't matter. Your search will be just as slow because it has to wait for everything before proceeding. So this is with GC so far, right? But I think the moral of the story really, especially when trying to do this kind of optimization, is that you have to look across the stack. I mean, anything right from a kernel tunable for the Linux kernel right down to how you do queuing could actually affect your performance. things like, for example, the Linux kernel has a parameter called swappiness, which is quite important for sort of how it swaps in pages and out. Having an I/O scheduler which is fit for SSDs, like things like what is called huge pages. I won't go into details of these, and these are important. And on the other hand of the spectrum, doesn't matter how fast your Lucene search performance is and so on, if your queues are sort of small and you don't sort of notice that, you don't find out where your time is being spent, you're probably just being bottlenecked at some point even before the search is run. There are interesting places where we have found actually hard-coded numbers in the Solr which had to be sort of lifted because for the kind of like parallel searching we had done, those hard-coded limits were being hit. And then you realize that only this many connections are being made to a particular host, and it doesn't matter how fast your system is, it's only that it's going to be limited by that throughput. One interesting example, we spent around 4 months recently trying to figure out what the problem was there was an interesting bug with Jetty. Good news is that it's not there with Jetty 9, so if you're on the latest version of Solr after 5.2, you're covered. With Jetty 8, there's a weird bug where there's a one-off condition where every now and then it could actually stall without increasing the capacity it has till the last search request actually times out. My point is that you can't exclude anything. I mean, like even something which is like Jetty, which is mature and has had a lot of battle testing, could actually sort of trigger something that you didn't realize. So that's with the performance aspect of it, and that's only one half of the story really here, right? I mean, the other half of the story really is stability. And especially when running a distributed system which is as big as what we have, like we have thousands of cores in a cloud, there is a lot of potential for problems to appear. You're essentially looking at a distributed system which has 1,000 components, and that's no joke. We started with Solr 4.3.1. It actually had a lot of stability concerns, a lot of cloud concerns. Good news is that it's a lot better now. I mean, I wouldn't say it's perfect. I mean, there's still sort of like issues with the cloud which you can hit, but they are very there, right? And the challenge with us was that if there is a race condition somewhere, we will surely hit it. It doesn't matter how low it is in probability, we will certainly hit it. And if any kind of sort of weird edge condition, what happens if you can, is it safe to bring down multiple replicas of shard? You would think so, right? But there are race conditions around that. What if a merge is happening, right, just around the time a merge is happening, even if it is for less than a second, if you manage to shut down right in the middle of it, would you end up with a corrupted index? Yes, you can. No longer, but you could at least. And I think the overriding lesson here is that you will screw up, and you have to know that you have to be controlled about it. The worst thing which can happen, especially in a production system, is that you screw up, and then you make a bigger mess trying to get out of it, right? I mean, there's this thing called sort of zombie check in the Solr code, which tries to sort of ping each host to figure out if it is okay. We had the situation where one shard or one replica was particularly slow in responding, and what happened was that all the other shards and all the other nodes tried to sort of keep pinging in, hey, are you okay? Are you okay? This thing is already sort of like in a bit of a mess. And it actually spent more time trying to reply saying I'm okay or I will be okay, and it never ended up being okay. So even if it is a health check, it should be light enough so that it doesn't sort of like make a bigger mess of the situation. Will the cloud always heal after a network partition? Still cases where it just can't, where you have network disconnectivity. After some time, it comes back and then decides that nobody wants to be a leader of a shard and then completely shuts down. So it's an important lesson in life that Solr teaches all of us, that democracy can sometimes be annoying. Sometimes you just need to just step up and be a leader, come on. So I think we had to spend a lot of time apart from these, which is just stability, to just scale distributed coordination. There's something called an overseer in the Solr cloud which tries to coordinate all activity which sort of governs when the nodes go down and nodes go up. It's a single point which tries to do all of this, right? And when you have like hundreds of cores which are shutting down and starting up at the same time, it can become a bottleneck. There's a lot of discussions around cluster state. We have some people in the audience here who have been heavily involved with it. It's an ongoing discussion. None of this comes without any trade-offs. There are trade-offs either way. So it's an interesting discussion within the Solr community to how you can scale cluster state in multiple ways. I said, like I said before, leadership mechanisms have to scale. You have to, when some node goes down, it has to come back quickly enough, and leaders shouldn't gang up on some leaders because there's I/O impact due to a machine being a leader. And sometimes you can end up with situations involve 60,000 threads. No physical machine can really deal with that in an efficient way. But it all comes down to if you decide as a programming decision to add one thread per query on one shard, it can blow up pretty quickly. So I'm sort of like nearing the end of this presentation. As I said, like I very briefly touch upon something completely apart from search. So this is with search. The other big part of the system, which I won't be able to do justice in this talk, but to just give you a quick idea, so what is called alerting. Alerting is essentially the inverse of search. In search, you have like millions of documents, and then you have one search, and you figure out which documents actually match your search. In alerting, it's the other way around. You have like millions of searches, and then for each incoming document, you try to figure out which of the searches actually match this document so that you can inform those users. So there's no out-of-the-box support for this with Solr. There is actually something called Percolate in Elasticsearch you might have heard of. But actually, sort of like we ended up sort of implementing what Percolate did in probably a week or so in Solr. The problem is not that functionality per se, just that it's not scalable. All Percolate does for you pretty much, and this might have changed. I mean, I remember this from like a year or so back, is pretty much run a for loop around your searches. So you have an index of one document, you run a for loop against all your searches, find out which does. It's not scalable. We used a library called Luvac. There's an excellent presentation by Alan Woodward, who's a owner of, who's a maintainer of Luvac, called Turning Search Upside Down. He did this a couple of years back now at Dublin. I would certainly recommend you to sort of like go more into that if you need more details. What that tries to do is that it indexes your queries. So it makes a search index of your queries, and then pretty much tries to make a query of your document. So it's pretty much the upside way, and tries to run that query against your searches to figure out which searches could potentially match your document. Now, that's not an exact search. I mean, but all you can do is pretty much get a superset of queries which potentially could match the document. You could throw away queries which have no chance at matching your document. But at the second phase, you will still have to do the exact search. So that's where the for loop comes in, but it's on a much reduced set of queries to actually know for sure whether this query actually matched the document or not. So this is something that we built an application on top of Luvac called Baleen, and actually that's being productionized now. And we actually plan to release this application as open source, where what Baleen provides is essentially you can take your Solr schema and use that in an alerting application and actually get alerting out of Solr in a quick and easy way. In some sense, what we have done over the last 3 years is just the beginning, I would say, because what this has set the stage for us is to essentially get a search application which has sort of like wide community support, is sort of like we can control it in the way we want, it's flexible, allows us to do a lot of things. There's a lot more possible relevance. There was a talk yesterday by a couple of my colleagues on learning to rank in Solr. If you didn't attend it, I would certainly recommend you to go over the videos when they come up. What that allows, for example, is to have a very flexible way to score searches in Solr. And that really allows you to sort of like be very flexible about sort of like doing things like machine learning models, trying out with various features which affect the relevance, and be able to tweak your relevance. There are other interesting challenges that are just ideas at this point, really. This is something actually we're working on, trying to see whether we can get alerting on relevance sorted views. So you not just have like relevance sorted results in front of your screen, but you actually alert on top of that, so that as and when news stories come and your top 10 results change, it actually gets reflected on your screen. You can always make queries more expressive, and this is something that you can never stop doing. I mean, what if you had like, you have text which mentions an earthquake of magnitude Richter 6 was felt at some place? What if I wanted to search something like, I want to know about all earthquakes which happened near this place. I want a mention of Richter near some place, but I want Richter followed by the number 6 to 12. There's no easy way to do that. I mean, I'm pretty sure we can come up with something which sort of like does this in a very nice way, but these are kind of like challenges which remain. There's, of course, the problem of being able to do most read on any search. In our case, it's a lot more challenging because on one hand, we already have a very high commit rate and lots of documents coming in. In this case, for each document, you have like thousands and thousands of updates for every read that happens. Even if you batch them, it's quite a lot. So how do you do that? It's probably not even sensible to do indexing the way you would normally do, but have things like, for example, how can you update a document in place? Ishan here is actually working on one of the features to be able to update a document in place without having to reindex the entire document in Solr. That's our team here from Bloomberg. We started off with Solr like roughly 3 years back. I think Bloomberg had been using Solr even before that, but we as a new search team started using Solr. We have 2 committers. I'm a committer here. Christine in my team is a committer as well. Hundreds of patches, and challenges really are countless. And so the story goes. Thank you.